Okay, so a relation is a set of ordered pairs. And we can write a relation as a set, a table, a mapping, a graph, or an equation. If any of those are a function, then each element of the domain, in other words, all the x's of the relation or all the x's of the function, occur only one time in the table or in the set. Because they are paired to exactly one element of the range, which are the y's. So if I'm looking at a set of ordered pairs and I'm trying to decide if it's a function, all I needed to do is to look at all the x's and see if they're different. Because if they're different, I'm good. It's a function, right? If I look at a table, look at the x column on the t table, and I say, oh, all the x's are different, then I have a function. But if any of the x's are alike, it's not a function. How would I tell if a mapping is a function? Do y'all remember? You know what a mapping looks like? We're going to look at one in just a minute. Anybody remember the bubbles pairing up the x's and the y's? How do you tell if a mapping is a function?
Count the lines.
How many arrows are coming out of the x's, right? Because how many should they have if it's a function? Only one. Okay. How do you tell if a graph is a function?
The vertical line test.
Good. We're going to talk about that too, the vertical line test. All right, now a mapping shows how each member of the domain is paired with each member of the range. In other words, up here I've got the set, and then down here I have the mapping. All right, so let's talk about those. I'll let you guys copy these down as we go. I'll give you just a minute to get ahead of me, and then we'll go from there, okay? Okay, a mapping shows how each member of the domain is paired with each member of the range. So if I'm going to pair up, I'm looking at this set here. -3 is paired to 1. 0 is paired to 2. And then 2 is paired to 4. That's a pretty simple one. As a matter of fact, we haven't talked about this before, but this is called a one-to-one function. Not only is it a function, but it's 1-to-1, okay? There is 1x for 1y, but there's also 1y for 1x. If I'm going to define a one-to-one function, first of all, I'm going to say it is a function, and as you know, that has meaning. Those first two words, okay? That means it is a special type of relation in which each element of the domain is paired with exactly one element of the range. That's just in this word right here. So this is a one-to-one function is a function. Let's see, let me word that better. In which I would write this down if I were you. Each element of the range is paired to exactly one element of the domain. So it goes both ways. Each one of them are one-to-one. One domain or one abscissa for one ordinate for one abscissa. They are one-to-one. Not just a function, but a special type, a one-to-one function. All right, and then we see -1 is paired to 5. And then we see 1 is paired to 3. And 4 is paired to 5. Is that a function? Yes. Because each of the x's only have one arrow coming out of them. Is it a one-to-one function though? No, why not?
Because it doesn't have one-to-one.
Yeah, because 5's got 2, doesn't it? Okay. So this is a function because each element of the domain, all the x's, are paired to exactly one element of the range. But it's not a one-to-one function. All right, let's keep going. 5 is paired to 6. -3 is paired to 0. -3 is paired to 6. And 1 is paired to 1. That is not a function at all. So what do you call it? What do you call a set of ordered pairs that's not a function? It's just a set of ordered pairs. You just wrote it down. What is the word for a set of ordered pairs? Andy, what is it?
Relation.
A relation. Right, a relation. So this is just a relation. It's not a function at all. I've got pairings. I've got ordered pairs. But they're not one-to-one either way. So it's not a function at all. Do you guys understand that this X has got two arrows coming out of it? Or this ordered pair, those X's are the same? Y'all knew that, right? This is new though. This one-to-one. Do you understand that? It's a function, but like you were saying, they are one for one each way. Each X has one arrow coming from it. Each Y's got one arrow coming to it. And that's it. All right, let's look at these sets. Now what we're going to do here is we're going to give the domain and the range and tell if they're a function. We're going to do some of these for dollars, okay? But let's do the first one together. Now you'll have to forgive me here. Let you guys start copying these down. Just go ahead and do the first set and copy it down. You'll have time to copy down the others in just a minute. All right, but let's copy down this set. 2, 1, negative 5, 12, 8, negative 3, 1, 5. All right, from there, we're going to list the domain. We're going to list the range. Do you remember that when we do domain, we would only list the elements one time? Even if they occurred more than one? And we would list them in what order? That's right, least to greatest. All right, so looking at the X's, here they are, the X's. What comes first? Good. And then? 1 and, come on guys, help her.
2.
2 and 8. She got no help. Y'all understand? We were just looking at the X's, right? All right, now let's do the range. So what are we looking for now? Not the X's, but the Y's. All right, so here are the Y's. What would they be?
Negative 3.
Good.
1.
Good.
5.
Good. That's it. That's all you do. Now tell me, yes or no? Is it a function? Yes. All right, I want you to do the other 3 that same way we're going to do them for dollars, okay? All right, the first one is Andy. Why is that not a function?
There's more than one of the same things.
Right, negative 4 occurs 3 times, doesn't it? All right, next. Okay, so 1, 2, and 3, and the range is 1, 4, and 5, and that is, why is that not a function? Because of the
There's more than one.
The twos, yeah, right, the domain, more than one, two. Alright, so the domain -1, 1, 3, and 4, the range 3, 4, and 5, the range is repeated. But that's okay, right? It's a function, but it's not what kind of function? 1-to-1. It is still a function. Alright, does anybody have a question about any of those? Is that good? Alright, good job remembering. Alright, a graph or a set of points is a function if it passes the vertical line test. Do you guys remember that? Which way's vertical? Right, up and down. So if you draw a vertical line, it should go through one or less points on the graph. Okay, it might not hit a point at all, but if you have a line or you have a graph, if you have a graph, what kind of? Let me ask you this before I draw this. What is the only kind of line that's not a function?
Curved one.
Well, that's a curve, not a line, right? So what's the only kind of straight line that's not a function that wouldn't pass the vertical line test?
Vertical line.
Vertical line, okay. Remember, vertical lines are like the rebel. They don't have slope. They're not functions. They can't be written in slope-intercept form. So if I drew any kind of line, like if it had a positive slope, or if it had a negative slope, or if it had a zero slope, if it was horizontal, all of those are functions. They would pass the vertical line test. What about the parabola? Would that pass the vertical line test? Do y'all remember? What do you call that? That's a terrible graph. What do you call that? Starts with a Q. A quadratic function. And the graph is called, starts with a P, parabola. Does that pass the vertical line test? Yes, it does. But on the other hand, I'm not even going to try this. I'm just going to. Circle. Is that a function?
No.
It doesn't pass the vertical line test because when I drew a vertical line through there, I would hit 2 points if I drew it in the middle. Now you don't try to draw it on the outside so that you can hit 1 point. So if you say it's a function, you don't do that. You try to prove it's not. And when I draw a vertical line through there and hit 2 points, I can say it's not. So that's what the vertical line test is used for. Alright, let's talk about function notation. Equations that represent functions are written in function notation. The symbol f of x replaces the y and is read f of x. If you'll remember, that does not mean f is times x, right? That means the name is f and the variable used inside of it is x. So this is an example of a linear function because let's look, if I took the y and put it in that equation, you could tell me that it was written in what form? Look at it carefully. Y equal mx plus b. What form is that? Slope-intercept. All right. So that's written in slope-intercept form. It is a function, and so in the place of y, we put f of x. And remember, all that means the name is f, the variable used in the problem is x. So what they've done is what's called evaluate the function. What does evaluate mean? Think about word wall. What does evaluate mean?
To solve?
Plug it
To
in,
comprehend.
solve. Right, to plug, what?
To comprehend.
If you evaluate something in math, though,
Oh, okay.
you plug in to whatever you've got and solve. So if I'm finding f of 4, that means into the function f, plug in a 4. Okay, take the x out and put a 4 in its place. Okay, so instead of 2 times x, I've got 2 times 4, which is what? 2 times 4, come on.
8.
8 plus 1 is 9. We evaluated that function at 4, but my answer was 9. Alright, so if this is my function, if f of x equals 3x plus 2, let's work together and do f of 6, and then somebody will do f of 3 for $1, okay? So we're gonna do this one together. All right, f of x is 3x plus 2. Together, let's find f of 6. F of x is 3x plus 2. We're going to find f of 6. And so in the place of x, I'm going to put a what? It tells me right there, a 6. So 3 times 6 plus 2. What is 3 times 6?
18,
And what's 18 plus 2?
20.
That's it. That's all you do.
So you just plug in where the X is.
Right, and then just solve it. You know, like you were saying earlier, just solve it. All right, so you guys find f of 3, and then we'll do it for $1. You guys agree?
Yes.
Easy enough, right? Anybody have a question? This easy? I couldn't think that's hard. All right, I'm going to give you a quiz on these in just a second. So let's talk about them again. We kind of introduced it earlier, but we're going to do it again here. Go back to think about your parent graphs. Okay, this is a linear function. Why? Because it's a line, like we were talking about earlier. You know, curves are curves. Lines are straight lines. And it's always a linear function when it's in the form of a line. Think about the root word there. And so it can be written in this form like limit x plus b when it's a function. This one you haven't seen before, and I don't know how well you can see from where you're sitting, but this has little steps, like stair steps. And above each dot there's an open circle. Then there's a closed circle. So what that means is that this is open. This is not a point on the graph, it's open. So would that pass the vertical line test if I drew a vertical line right down through there?
Yes.
Yeah, because it would only hit that point, because this one's open. Do you see why it's called step function? Because it looks like steps. And the equation is written with what you might call a bracket, and you have never done that before, and we won't do it unless you take Algebra 2. But this is the greatest integer function, and it's written with steps.
How does that work?
Because let's think about it. You know this is 1, 2, 3, 4, 5, 6, 7, 8. Those are the integers. What occurs between 1 and 2, and 2 and 3, and 3 and 4?
0.5.
Fractions and decimals. All right, if this is the greatest integer function, all the answers have to be integers. So that's why none of those lines are between any of those integers. They have the answers, the
What I meant
y's.
was like, why doesn't it take a step up, like up 2 integers and
Okay.
then over 3?
Y'all remember he asked, okay? And what is the greatest integer that's not greater than 2.5? Well, 2.5 is between 2 and 3. Which one of those is not greater than 2.5?
2.
2. Okay. What if I do 2.9? Is it the same thing?
Yes.
Okay. What if I do 3.1? Where does it go? 3. All the way to 3.9? And so it'll stay here at 3. It stays here at, well, not 3. It stays here at 5. Stays here at 7. Stays here at, it's going to stay, see, it's on that integer. Good question. But
So
that's
you're
why
saying-
it's in steps.
So you're saying there's going to be a
And-
ton of brackets when you try to graph one of those?
Mhm. And that's why this is open and this is open and that's closed, because it jumps from that step to that step. It jumps up to an integer. All right, you guys know this one, right? Remember? Y equal absolute value of x, the absolute value graph. You know, this one's what we were talking about, what you said it a while ago, but it's you too, right? It's y equal x squared. It's quadratic. It is a parabola. That's a cubic function. Now, the one that we did looked more like, this. It actually didn't have all this little extra right there. But that's a cubic function. It's got an x to the third in it. You guys remember this one's got a square root? Remember that? Remember what, broken arm? Didn't we do it that way? Good. And then this one is exponential. Let's talk about that. An exponential curve always does the same thing. It approaches a line like the x-axis, but it doesn't touch it. and then it shoots to positive infinity this way. This line, the x-axis, is acting like an asymptote. And you say, well, what does that mean? An asymptote is a line that a curve, a graph approaches, but it can't touch it. It's kind of like having an electric fence in math. You have a little calf, new calf, wet nose, goes up to the electric fence and does a little sniffing around, and then bam, right, gets hit, right in the nose. What does the calf learn? Don't touch that thing, right? Don't touch that again.
I got told that one was off, and I grabbed a hold of it.
And you learned that it was.
Yeah, I haven't touched one since.
And you don't. You learned, didn't you?
I was
All right,
like,
graphs are the
yeah,
same way. This line's like, I am not going to touch that line right there. That is an asymptote. I'm going to get real close to it, but I'm not going to touch it. And I'm sure I'm going to cross it. All right, let me see if you guys can do better than one of my other classes did today. I'm going to ask you a question, and it's a thinking question. So you got your thinking cap on?
I left it.
Every time I make a move, I'm going to, is it time for the vote? You never can tell in here, can you? Every time I make a move, I'm going to go halfway or half of the distance to the door. That door. Am I ever going to get to the door? All right, I'm going halfway. I'm going to stop. Let's say this is halfway. Okay, I'm going to go again. I'm going to go halfway. Am I ever going to get to the door? I'm going to go halfway. I'm going to go halfway. I'm going to go halfway. I mean, I could touch it if I wanted to, right? But half of what distance is 0? John, I'm not going to get to the door, am I?
No.
Theoretically, I'm not going to get to the door. Because half of what number is 0?
Half of,
Only 0. Like if I had started at the door, I'd be at the door. But if I kept going halfway every time, can y'all understand that I would theoretically not get to the door? Because half of what number is 0? Only 0. So that's what it means on the graph by approaching. I'm approaching that door. As a matter of fact, I'm close to it, but I'm not going to get there. All right, we'll pick up there tomorrow. You guys have a great day.